quickly go over the applications of Scenic, and then Sanjit will come back and then give sort of ongoing and future work that we're doing regarding Scenic and VerifAI. So hi, my name is Edward Kim, I go by Eddie. I'm a postdoc in the East Department at Berkeley, advised by Sanjit and Rest of your environment. So let me cover Scenic and VerifAI, how they're applying. So in particular, I'll cover three topics. First is regarding sensor data collection. So how do you actually do that using Scenic? And then second part is sim to real validation, meaning, okay, so you use this synthetic data using Scenic in different simulators that you're using to test your autonomous systems. Can you really trust that result? Meaning, let's say you found a failure. Is that perhaps a result of a spurious artifact that is in synthetic data, but not present in the real data? And how do you actually differentiate between those two? So that's what I mean by sim to real validation. And the third part is testing different aspects of the autonomy, like perception, or behavior prediction, or planners, where increasingly machine learning models are also being used with VerifAI. So let's look at the data collection part first. So we are using Scenic, depending on what kind of sensor data collection capability that your simulator requires. As you know, Scenic is simulator agnostic, so it's not developed for a specific simulator. Depending on which simulator you use, for example, if it's Carla, it allows you to collect these type of semantic segmentation labels along with the RGB data or depth image or other types of labels such as 3D bounding boxes or LiDAR with labels, which are really expensive to collect in the real world, but you can actually get those using using Scenic along with your simulator. And again, to reiterate, the fact that you can use Scenic now means you have full control over the content of the data, right? So the fact that you can craft the scenarios that you want means you can generate those scenarios in simulator that you're using and generate the sensor data based depending on the capability of the simulator, right? So how do we actually do this? So Daniel actually recently implemented sensor data collection with formalizing the syntax in Scenic. So here, I just want to quickly set it up. Here's our ego car, and there's the other car. So ego is at a spot, which is uniformly on the lane. Then you pick a spot that is at a center line on the lane. And then there's another car that is offset by the ego car so you're placing that car 10 to 30 meters ahead of the ego car. So this is a sort of the scene right now. And here you specify the data that you want to collect. So you say ego, comma, with sensors. And then in this case, you want to collect front segmentation data. So he's calling different sensor data. So RGB sensor data or segmentation, LiDAR segmentation sensor data. And then these offset is basically, okay, where do you want to place the sensors on the vehicle? So with respect to the center, I'll place it on the 1.6 meters and then 0 and 1.7 offset in XYZ coordinates. And providing different attributes to save those sensor data in certain format. Yeah, so, and then here, you specify, okay, so here you're specifying what sensor data you want to collect. But you didn't actually specify that you should record those sensor data. So here is a format that you would use to specify how to record it as. So here you're calling this front SS where you define over here, and then say, okay, after 5 seconds from the beginning of the simulation, every 0.5 seconds, save this data that you observe about the ego to this format. So it's going to be a JPEG, and then it's the front SS underscore time, and time is the simulation time that you're collecting. And likewise, similarly for RGB. Any question? So this is just implemented. So since you're at the tutorial right now, you are anyone?
Oh, finish your sentence.
Okay. So since you're at the tutorial, you're kind of getting first access to the functionality that is coming up. But we'll be adding the documentation in our public website soon, so you can make use of this.
All I'll mention on this one is that this example, which Eddie is going through, is in the repository, but it's not in the main branch yet, because as Eddie said, this is like new stuff. It's on a branch called sensors. So if you want to try it out, you can check out that branch. And it works in Carla right now. But the reason we have introduced this syntax is, again, because we want to have a simulator agnostic way to specify these things. So here we have these generic semantic segmentation sensor and RGB sensor classes, which once we have implemented this for the other simulator interfaces, will work just as well in, say, MetaDrive as they would in Carla, so that you could run this driving scenario in either simulator and collect these images or the video in the case of our RGB without having to worry about details of whatever simulator, whatever the APIs provided by those specific simulators are.
Then,
Yeah.
so the next application domain is sim to real validation. So again, question is, let's say you tested in simulation with these synthetic sensor data that you generated. How can you actually trust the result, right? Because you can actually see the difference between synthetic RGB and the real RGB. And how would that discrepancy result in the different behaviors of the autonomous system? Right. So therefore, can we always trust the results of the failures of the system that we find in simulation? So how do we actually differentiate that? Well, the current status quo is actually, okay, let's go out and try to replicate that situation manually, and then see if that results in a failure. So that's what we did. This is what Sanji showed you before. And we replicated this scenario multiple times. And then, okay, in some situations, we were actually able to replicate that failure. That's great. But what is the issue with this? Very labor intensive. Here's Sanjay. I'm the one taking the picture right now, but every time this pedestrian fell, I had to go there and put it back on and then reset this scenario. It's so labor intensive, which means it's not scalable. You can't test, you can only test so many scenarios in one day. It's not a scalable course. So we were wondering, okay, can we make this scalable? So our approach was the following. Okay, well, suppose we identify failures of a ML component, whether it's perception, behavior prediction, or planning, in simulation using the synthetic sensor data. Okay, so let's encode that failure as a scenario program using Scenic. And then nowadays, across academia industry, there's a lot of there has been a lot of effort behind collecting real-world sensor data, but also labeling as well. So there are a lot of open source data like new scenes and so on that are out there that are labeled. And so the question is, okay, if we can, so from this real-world data set, if we can find a matching subset of this real-world data set that matches the description of the scenario written in this Scenic program, then we can now test this ML model with those real sensor data, whether it's RGB, LiDAR, whatnot. And then to validate, okay, this failures that we found using the synthetic sensor data, and we replicate that on the ML model using the real sensor data. This way, you don't have to actually go out there and then try to replicate the way we did before. So this work, we started off by, in 2022, about querying the labeled images, static images with scenario programs, which was published at ICCPS 2022. And then recently we also published a paper that extended this query into videos, time series sensor data as well.
So does it mean that you find a failure case from this, Scenic and try to figure out whether there's a similar kind of signal failure also shows it is this real world case, and then you ran the Scenic of this real world case and see whether that appears or not.
Exactly.
So it sounds like it sounds like it underlines that this kind of real world data set is really speaking now that almost all the failure case from this Scenic can somehow be figured out corresponding case in the real world.
It's possible that this query may result to be extreme like empty system. That's also possible too, right? But then what does that mean? That's also a valuable finding in a sense that, oh, we've identified a failure scenario, which is now reflected in the potentially this, like let's say this was a training data set. It was not reflected in the training data set. It's not something that we encountered so far, right? So that itself is a valuable finding as well, right?
Yes.
And like as you know, Eddie was saying before, because it's so difficult to collect real world data, that targeted scenarios, right? It's easy to stick a camera in front of a car and then, you know, from dash cam videos, whatever, get lots of data that way. You could even try to automatically annotate some of that. But you could use this at least as guidance to say, maybe there are particular areas we should put effort in to do more testing because they are not adequately represented in the existing data, and they seem to correspond to cases where, at least in simulation, the system did something undesirable. So it may now be worth putting in that effort to see, is this a real failure case or it's just some artifact of the simulation? If that makes sense.
Right, so I'll move on. And I'll actually skip these experimental results section in the interest of time. Under this, or okay. So for example,
Oh, he's going to be back. He's not up until 5:20, right? So
oh,
yeah.
okay.
So it's okay. You can.
Okay.
Yeah.
Okay, so as part of the experiment for this work, so here's a Scenic program. We compared with the existing vision language models. So here's a Scenic program. We feed in the Scenic program to our query algorithm, and then also provide the time series labeled sensor data. And also as a baseline, we provided a description, natural language description of this Scenic program, and then also provided the time series labeled sensor data to a vision language model. And then we asked, okay, so is this, the problem is this sensor data in the support of the distribution modeled by the Scenic program? When I say support, it means the probability of this sensor data matching this program is greater than 0. So we're asking this true false question. And then we're comparing that with results. And so when we compared using the baselines were Claude, Sonnet 3.7, and then GPT-4o, that was what was the best one out there when we were running this experiment. And then the accuracy is shown here. So 100% would be out of 1. 1 means its accuracy was perfect. And then the average runtime of running this query is shown here underneath as in seconds as units. And what this shows is that we ran this across 4 different Scenic programs or scenarios. And we show that on average, our algorithm is near 80% in terms of accuracy compared to GPT or Claude, which is 60% and 44% in terms of average accuracy. And then in terms of also the average runtime, our algorithm is orders of magnitudes faster. So the message here is that by leveraging the labels of the sensor data that are already out there, you can actually query and identify matching sensor data more accurately and also much faster. All right, so what does that mean? So let me show you an example. So here is a scenario where there's an eagle car. Let me just show you a very simple example. Here's an eagle car and then other car. So eagle is on the road and then other car is on a lane that is visible to the, so this other car is on eagle's lane and it's also visible to eagle, meaning it's in front of you. Okay? And then in this case, other car is just stationary. So other car is in front of eagle and is stationary on that lane. And then eagle behavior is by default, you're gonna follow the lane, but when the distance from the eagle to the other car is within uniformly randomly 1 to 15 meters, it will trigger that eagle will trigger lane change. And then once the distance is lower, it will follow the lane. So, for example, when we query a real labeled time series sensor data, with that Scenic program, it results in
Muted here.
identifying sensor data like this. Yeah, so here's a car in front stationary, the US triggers lane change, and then follows you. And then we're retrieving these data. So on the left side is the RGB, on the right side is a LiDAR of that same scenario, which are all labeled, as you can see. So again, are you? Thank you. But the point is, using this approach, we are actually querying complex, potentially more complex scenario that involves multiple agents interacting with each other in this physical domain, which is still a big challenge for vision language model. Okay, finally, formal testing of CPS with Scenic and VerifAI. So I want to start with the question of why do we need VerifAI in the first place? What is the what kind of challenges is it trying to address? So from Scenic program, we use a Scenic simulator to generate sensor data with labels to test ML components. And Scenic program, as you know, is defining a distribution of scenarios. The question is, how should we sample or search through this distribution? And so, just to through exaggeration, just to give you an idea, let's say a sampler can hack. So let's say you found the failure scenario, concrete scenario by sampling from this distribution. And then since if the objective is simply to maximize the number of failure scenario, it can hack by sampling that exact same scenario over and over and over, right? That could be a hacking. So if that's exploitation. But at the same time, that's not the only thing that we want to achieve. We also want to find not only just failure scenario, but diverse types of failure scenarios. Right? So there's a trade-off between exploitation and exploration of different distribution of environmental variables that are specified in the Scenic program. So how do we balance out these trade-offs? Those are the kind of challenges that we're looking at in the VerifAI. So Sanjay covered this, but it has its search for sampler inside that we support, such as Bayesian optimization, multi-arm bandit, cross-entropy, simulated annealing, Halton, and so on. But you can also add your own samplers too, if you have your own. Right. So that's what VerifAI does. And then suppose you have your own ML model. That's in that case, in addition to the synthetic data collection Scenic program that I showed you, you can do something following to evaluate your ML model. So you can import. So this is the same Scenic program that I just showed you a few slides ago. At the top, let's say you're using PyTorch. It could be something else, but PyTorch, and then you load your ML model, whatever that is, behavior prediction, planner, perception. And then you're collecting these sensors. Then you here line 24 and 25, you're recording those sensor data. Now in line 26 to 27, you're gonna hold those sensor data, input it to the ML model, and then save the output of that model every certain frequency, in this case, 10 hertz. And then, in verify, when you're calling it, this is all templatized and documented. But here, you're specifying in verify what is the evaluation metric. So since you're saving ML, the output of the ML model, given the sensor data at every 10 hertz, in 10 hertz, you can call those recorded output. Let's say in this case, you're measuring intersection over union. Then in this case, you can compute, let's say you're interested in the mean IOU, average of IOU. Then you just go over those recorded output and then compute the mean of them, and then report that using Scenic, using Verify. So I just wanted to show you an example of how you would generate synthetic data and use that data to test whatever ML model that you have, in-house ML model that you have, to compute an evaluation metric of your own. So a demo in this case is that, let's say, in this case, we're interested, we want to identify situations where, so this is a scenario where ego car is the car in front, and there's a badly parked car on the side, which would swerve into the ego's lane as ego's driving forward. And the specification in this case is that the distance from the ego to the car in front should be always greater than certain safety distance. And after running verify, it actually records all the, so it generates the CSV file that you saw. It's an option that you can do. And if you load it, you can actually see all the environmental variables that are sampled from the distribution of the Scenic program. And then, and also the evaluation metric that is computed. So in this case, it's showing what was the RGB color that was sampled, what was the position of the eco car that was sampled, position of the other car that was sampled, time of day, all of those, as well as what was the minimum distance between the ego car and the other car for each simulation. So, yeah, that's all. Do you have any questions? Yeah.
Since the data query, first question is how do you convert the Scenic program to the language?
For the experiment part?
Can you repeat the question?
So the question is for the sensor data, the video sensor data query work. How do I convert the Scenic program into natural language instead? For the experiment set part. Oh, that was done manually. So yeah, for that experiment, we just did it manually. So yeah.
I have a question here. So when you into comparison with the large language model, so the input to the large language model is a description of the disabled learning. How we can construct the say and where the car is, like that, which have something like that maybe, and we will test it on Scenic, it's a simulator, run just like run a bunch of trajectories in this Scenic as in this case. It seems like it's not an apple-to-apple comparison.
Should I take that one, Eddie, or?
Well, so the question is, for the video query works, the same sensor data query work.
Yes.
You're saying on one side, you're using the Scenic program
Yes.
to query over the real sensor data.
Yes.
And on the other side, you're using the Scenic, for the testing part, you're using the Scenic program to generate those scenario in simulation.
I think what he thought was that the way that our querying algorithm works is actually running simulations.
Yes.
So it actually doesn't run simulations. So we can clarify that. But you're right that the comparison is not apples to apples because the input to our algorithm is a Scenic program. And the input to the large language model was an English description of the scenario, right? That Eddie wrote. So yeah, we could not do a direct apples to apples comparison because there was.
Single project such a framework that.
Right, that's right. There was no other tool that would take a Scenic program and do this querying problem. It was a new problem that we were proposing, right? This was meant to show like without a specialized algorithm for this problem, one approach you could try to take would be to ask a general model like a VLM, querying it in a natural language instead of with Scenic, right? And that has pros and cons. But basically, what we were trying to show with this example was that you can get more precise querying if you have a specific Scenic program, which is not ambiguous the way natural language would be, right? And a specialized algorithm that can use that as the format for the query. But it's not like a direct comparison because they are solving different problems.
So it's okay.
Okay.
That's all make clarified.
But then to the issue about running simulations,
Yeah.
I think Eddie didn't have time to go into it, so maybe he could describe now a little bit more if you're interested, but the algorithm does not actually run simulations. We assume a way of classifying trajectories into certain kinds of primitive behaviors, like this is just driving in a straight line versus this is a lane change, right? And so we have some particular way of doing that classification here, but assuming we have a way of classifying trajectories in that way means we do not have to actually run trajectories in a simulator in the query algorithm. Is that right, Andy?
Yeah.
Because unlike the static images, the first version that Eddie talked about was for static scenes, and there the semantics is purely in Scenic. Like the Scenic program defines precisely a distribution over scenes. The semantics is actually in our paper, like there is a specific distribution over those, and you can query that. But for dynamic scenarios, remember, Scenic just says what actions the agents take as a function of the state of the world. But what we are getting in the data is not actions, it's trajectories. And turning the actions into trajectories is what requires a simulation of physics, right? That Scenic uses the simulator for that. And depending on the simulator, you have different physics models, you could get different realizations of that same Scenic program, right? So that's why, in order to go sort of like backwards, so to speak, from the trajectories to the behaviors which could have led to those, we have this labeling step or the classification step, which was done by an ML model, I think, in the papers, right? Yeah. Yeah.
We can also talk more.
Finally, on the image of, on the slide of, you see, targeting, fit to a human at that side. I noticed that the difference between the accuracy of, the percentage of, wells and force. Yes, you see the percentage of 62 is different from the percentage of -3. Why it's a safe case and an unsafe case have such big difference?
I think I talked about this in the first part when I presented this, but I think the paper talks about this a little bit, but one of the issues is the LiDAR fidelity. So the LiDAR in simulation is very low fidelity for performance reasons. But the real LiDAR is much higher fidelity. And so as a result, many collisions that we saw in simulation don't actually appear in reality because the real sensor is better.
I think another factor in this case is that most of the unsafe scenarios we found were on the edge of being unsafe, right? It's not like the car just plowed into the pedestrian at 20 miles an hour, right? It was more like the video that Sanjit showed where it just barely hit the pedestrian, right? And so if there is a small discrepancy between the simulation and reality, it's more likely to change the result of these failure cases than the safe cases, which tended to be more robustly safe, right? And even in addition to like what you might call the classic sim to real gaps, like the sensor data is not quite right, the physics model is not quite right, there were other major gaps coming just from the difficulty in the experimental setup. So like here, I mean, Eddie mentioned, I think we could only run a few dozen of these over several days at the test track. And part of that was even something as simple as driving the autonomous car to the exact point that it started from in the simulation is very difficult, like getting it to within, centimeters of the exact same point,
Yes.
right? So even if the sensors were perfectly modeled, even if the physics was perfect, just recreating the circumstances from the simulated scenario in the real world is difficult. So there's always going to be some discrepancy there. And if the collision was just barely grazed the pedestrian, a small gap like that could make the difference between a safe and unsafe.
Another question, when you have a scenario with a pedestrian involved, do you need to like model the dynamic of the pedestrian or something like that? Is that possible, like you cannot accurately predict it because you cannot accurately model the behavior of human because is that part of the reason coming from that set?
Right. So
Factor?
the question was, is there a factor from difficulty in modeling the human behavior in
Yes.
this case? Absolutely. So, I mean, in this example, I'm not sure we actually had time to Sanjit showed the snippet of the code briefly. It was this hesitating pedestrian scenario where the Scenic program defined a specific behavior for the pedestrian where it walked forward for some random amount of time, paused for some amount of time, and then continued. So we put that in as a class of behaviors to look at where we varied those parameters of how long to hesitate and so forth. But that was a specific class of behaviors that might or might not correspond to how a real human would behave, right? So in this case, there was also definitely a discrepancy there because like we thought this pedestrian, there's like a box with a conveyor belt to pull it, right? We actually thought it was programmable so we could put in those same timings. Turned out it was not. So I think for at least some of these, we had to like manually press a button to cause the pedestrian to start going.
Yeah, I mean, there's many sources of
Right.
a sim to real discrepancy. And in spite of that, I think what this slide is saying is
You could still
we
get
saw a pretty good qualitative
equation.
match.
Right. Right.
In safe versus unsafe.
Right. But and like as far as Scenic is concerned, you can plug in any kind of model that you have for human behavior. So this was a very simplistic one, right? But you could, because we were trying to look at a specific situation that we could model on the actual test track. But for simulation, you could plug in some complicated model, maybe learn from data, for example, like people have used imitation learning to produce models of how pedestrians move, for example, right? And it's easy to invoke those sorts of models from Scenic so that you can get human-like behavior of pedestrians, for example, and test your system against those.